Hello, and welcome back to A Slice of Physics.
We are now ready to discuss free body diagrams, which is an important tool in solving motion problems in physics. Essentially, a free body diagram represents our object of interest as a particle or a dot and shows all the forces acting on the object as vectors. Seems pretty simple, but it takes some practice to get this method down. So let's get started with some examples. So our first example is to analyze the motion or the state of motion of a ball that's hanging from a string that I hold in my hand. So starting with the picture, let's say that's my hand, here's the string, and here's the ball that's hanging from it. Our object of interest is the ball. In order to show the forces acting on our object in a free body diagram, we got to first identify the forces. So going back to our previous video, we do that by first drawing a closed loop around the ball and then going around this loop to see where there are interaction points where forces are applied on the ball. So as we go around, let's start the journey here, and as I go around all the way here, there's nothing in terms of interaction and forces, but when I get to the string, there is a force of tension that acts in a pulling direction, so in this case in the upward direction. So we only have one contact force in this example, and we have, as usual, the force of weight, which is a long-range force acting down. So now, with this ball just simply hanging off of the string from my hand and being here at rest, it's simply obeying Newton's first law. It's not changing its state of motion, which implies that there is no force acting on the object. Well, we know that there are two forces acting on the object, but the net as result of those two forces has to be zero for it to be in equilibrium. So in order to draw the free body diagram, we show the object of interest as just a dot and show the forces as vectors. So I'll begin the tension vector here and show it acting upward like so and label it T, and I'll show the weight acting straight down and label that as a W. Now you notice that when I drew this, I showed the length of the tension vector and the length of the weight vector as equal. I had to do that because the magnitudes of these two forces have to be equal, and with their directions being opposite, they cancel each other, and the net force on this ball is zero, which corresponds to its state of motion being at rest. So if I wanted, I could just write that down here and say the F net in this case is zero, and the acceleration of the object is zero. So there we have it. Here's the free body diagram. It shows the object as just a dot and removes all of the external environment settings and replaces them with just the forces that they apply on the object. That's why it's called a free body diagram. It only includes the object and the forces that are acting on it. Okay, to move forward on this, let me take a different example. Let's now say that I take the ball and I swing it from left to right, and we take a snapshot of the situation when the ball is at the highest point on the left end of its swing. So there's the picture of the situation. And once again, I'm interested in drawing a free body diagram of this object, which is the ball. So our process starts as usual with drawing the closed loop so I can identify all the forces on our object of interest. And as I go around the loop, once again, I only have the one contact force of tension. And now, since tension is a pulling force applied by the rope, it will act along the direction of the rope, so it'll be in that direction. And I have the weight, which acts straight down towards the center of the earth. So now, in this situation, we took a snapshot of the ball at the topmost end, and we know that the ball is going to start swinging back down. So it's going to have a net acceleration that points in this direction as it speeds up, moving down. Let's keep that in mind as we develop this object's free body diagram. So once again, I represent my object as a particle, and I show my forces here. So tension acts this way along the rope, and weight acts straight down, and I'll show it like that. And let's label them T and W. Note that while the weight is the same as before, the tension now is lesser than the weight. This is because these vectors that are shown on the free body diagram represent two things. They represent the direction of the force, and they also represent the magnitude. And even though we don't have an absolute scale, the relative lengths of different forces shown on the free body diagram are important. And what I'm trying to convey here is that the tension in the string is less than the weight of the ball. Well, why is that? Let's see what happens when I add these two vectors. You know the geometric way of adding vectors, so I'm going to grab that tension vector there and drag its tail to the tip of the weight vector. So it would look something like this. And when I do that, the net force, that's the addition of these two, is going to act in that direction. So here's my F net in this case. Does that fit our situation here? Well, this ball is sitting here for an instant of time before it starts coming back down. And as it comes back down in this direction, it's going to speed up in that direction. So it's going to have an acceleration in that direction. And since we know that the acceleration's direction is always the same as the direction of the net force, that matches what we have here. So even though the free body diagram could be stated very simply, all we do is identify our object as a dot and show all the forces acting on it. We got to make sure that as a first step, we identify all the forces acting on the object, and then two, show them on the free body diagram as vectors, which means we got to show them in the correct direction, and we got to show them with the correct relative magnitude, which would be the relative lengths of the arrows. And what's correct has to fit with what is happening with the object. So in our first example, the object was simply in equilibrium. It was following Newton's first law. So the net force on it had to be zero. So the length of the tension and the weight vectors were equal. In the second case, we knew that this object was now going to accelerate down in this direction. And so it had to have a net force that pointed in the same direction, which led to the fact that the tension in the string is smaller than the weight of the ball. Now I'll just make one last point relating to free body diagrams that will be useful as we go forward. You notice that when we show the forces, we start the vectors at the object. So let's say I have an example here where I've got a box that I'm pushing along the floor, and here's a partial free body diagram of this object. There's a temptation to show the pushing force like that, because intuitively we think that the force is being applied in that direction, so this would be the right way to show it. Well, this actually turns out to be wrong because it does not follow our rule that all of the vectors have to start at our object of interest. So the correct way to show this force on a free body diagram would be like so. So the force vector acting towards the right starts at the object of interest and extends in the direction that it's applied and has a length that corresponds to its magnitude. Now, of course, there are other forces like weight and normal force, but I'm not showing those right now because I only wanted to make this point about how to show the vectors starting at our object of interest. Okay, so that wraps up our first look at free body diagrams, and in the next couple of videos, we'll get some more practice with this.